Good day, everyone. This is going to be the video lecture for Chapter 8 for Physics 1000. This will be the last new chapter before the next test. This test will be available to be taken for the first couple of days next week. So basically you just have to take it before midnight on Wednesday. Monday, up until you take the exam, our class calls will, up until you take the test, up until you take this test, our class calls will be set aside for review, studying, making sure that everyone is good with this content before the test itself. Test will work the same as the last one. Basically, at any point before midnight next Wednesday, you can email me. I'll send you the file. You work on it. You send me pictures of both your answers and your work, and make sure that they are scans or pictures high enough resolution for me to be able to read them. And then I will get your grade back to you as soon as I can. So you just have to take the test by the end of Wednesday. And at any point during the test, please call me, and ask me into a group Google Meet call, email me. I will answer any question you have. Okay? Also, never leave anything blank. I give a lot of partial credit for literally anything. Never leave a question completely blank. That's the only way to get 0 points for a question. After the test next week, we will have a couple more additional topics, just small sections about a little bit of the basics of electricity, because it's important enough for you to live on Earth. A little bit of the basics of waves, because it's, again, important for you to know to live on Earth. And we'll wrap up the week bringing everything together, reviewing for the exam. Exam will be Monday the 29th, which I will also be available to assist you with absolutely anything. Please come to the class calls if you have questions, even if you don't have questions, just for review. If your schedule is not letting you make the class calls, let me know. I can hold extra ones. I can move them around. It's your responsibility to make sure that you can get to me with your questions. Now, Chapter 8 is going to be the last new thing going on to this current test. So the day this is going up will be Friday, and Monday. You can take the exam Monday if you're absolutely ready for it, but I have Monday set aside for exam review stuff, test review stuff, and then we'll move into, I've said I want to dedicate Tuesday and Wednesday to the test and questions with the test, and then a couple days after that will be a little bit of the new topics, just closing final things that you need to know as part of physics, and then we'll move into finishing out the course. So let's talk about Chapter 8. This is also going to be pretty heavily concept focused. So let's just go ahead and get started. Slide 1, title slide. This is going to be about thermodynamics. That is the study of basically how heat moves and the things that heat can do. Now, moving on to slide 2, we have listed here the laws of thermodynamics. These are very important physics principles. You've heard of Newton's laws. Newton wrote 3 laws of motion that are very important to how we understand physics on Earth. These laws of thermodynamics are also incredibly important for our understanding of energy. Now, we tend to say the 3 laws of thermodynamics, but there are technically 4 of them. We added one before the first law called the 0th law. So normally we have first, second, third. Well, now we have 0th, first, second, third. So really there is 4 of them. We're just going to talk about them really quickly, and then we're going to expand on them as the slides go on. So the 0th law of thermodynamics is the easiest one to understand. If object A and B are in thermal equilibrium with object C, so the black marker is at the same temperature as the dinosaur. The red marker is at the same temperature of the dinosaur. That means the black and red markers must also be at the same temperature as each other. If the black marker and the dinosaur are both at 25 Celsius, the red marker and the dinosaur are both at 25 Celsius, that means both the black marker and the red marker are at 25 Celsius. It's just the commutative property of temperature, basically. Next is the first law of thermodynamics. This one says that energy cannot be created or destroyed. This is a statement you are familiar with. We call it the law of conservation of energy. The universe as a whole has a total amount of energy within it. That energy can change forms. You can change what type of energy it is. For example, if you drop a falling object, it has GPE, which will turn into KE as it is falling. So you can change what form the energy is in. You can also change what object the energy is in. For example, if you throw one object at a second stationary object, when they collide, you will transfer energy from object 1 into object 2. But throughout all of this, the total amount of energy present in the entire universe and within the closed object system remains the same. And that is what the first law says. Second law says that the entropy of the universe can only either stay the same or rise. Entropy is the physics way of saying chaos or randomness. And so disorder in the universe is always rising because every single act you ever do creates some thermal energy. Because of friction takes mechanical energy and turns it into thermal energy. You can feel that by rubbing your hands across one another, and they warm up because some of your mechanical energy becomes thermal energy in your palms. Every action takes some mechanical energy and turns it into thermal energy. Every single one. Every time you move, every time something else moves, anytime something is accomplished, some of the energy becomes thermal. And because thermal energy takes the form of the random movement of subatomic particles, that creates more randomness, more chaos in the universe as a whole. The amount of thermal energy present in the universe is constantly rising, therefore the amount of randomness and chaos in the whole universe is rising. It's theoretically possible for a process to not increase entropy, but there's no way for the entropy of the whole universe, for the chaos of the whole universe, to go down, because you cannot uncreate thermal energy. The last law of thermodynamics says that the entropy of a system at absolute zero, so when you are at the coldest possible temperature, the entropy of that object is zero. This is because when you're at absolute zero, you no longer have any thermal energy, your particles are no longer moving. If your particles are not moving randomly, there is no entropy in that object. Now, that doesn't mean that the entropy of the universe has gone down, just the entropy of that object. Similar to how you can take energy from one object to another, you can take entropy out of one object and put it into another. So you can reduce one object's entropy and eventually get it close to zero, but that entropy has to go into a different object, so the total amount of entropy in the whole universe either stays the same or rises. These are the laws of thermodynamics. They are very important for how we understand energy in the entire universe. And we're going to step through them all one at a time. Now on to slide 3. There's a quick definition here. A system refers to the objects in question, just the portion of the universe you are studying. If we were looking at a problem where we have two markers, they are in thermal contact with one another, and we are ignoring everything but these two markers, the markers would be our system. The surroundings would be everything else besides the markers. For example, my hands holding them. So just a brief couple of definitions. Slide 4 is Slide 4 is just more information about the zeroth law of thermodynamics. Again, if two objects are at the same temperature as each other and a third object is at the same temperature as the second object, the first and the third must also be at the same temperature. All objects that are touching, that are in a system together, will try to end up at thermal equilibrium and be at the same temperature. That's all the zeroth law says. Now, the first law of thermodynamics. We're going to get into a little bit of math here. So, energy cannot be created or destroyed. So, The total amount of energy in the universe and within a system has to remain constant. So, what the slide says, the increase in the internal energy of a system, that is the thermal energy of a system, is equal to the amount of heat added to the system plus the amount of work done on the system. The increase in the internal energy of a system is equal to the amount of heat added to the system minus the work done by the system. So, if an object is having work done upon it, when you do work on something, when I work on my chair, I am giving it energy. I am adding energy to it. So I'm losing energy and the chair is gaining it. I'm losing energy and the chair gains it. Meanwhile, if the chair was doing work on me, the chair's energy would drop because it is doing work. It no longer has that energy anymore. And so what this formula here says, delta U equals Q minus W. So let's define all of our terms. If we move on to the next slide, this shows definition for all of these terms. U is internal energy. This is the total energy that the object possesses in any form. Now, delta U is change in internal energy. And as the slide says, if an object's internal energy is rising, it is gaining more energy. Our next term is Q. Q, as before, represents heat. This is the thermal energy added into the system. I'm going to say this is positive if thermal energy is added to object. So if you add thermal energy to something, if you add heat to something, this is going to be a positive number. You are adding heat to it. Now, if we ignore this part right here, if you add thermal energy to something, its internal energy will rise. If this is a positive number, this is a positive number. So, ignoring everything else, if you add heat to something, its internal energy is going to go up. So, that's what the first part of this formula says. Now, there's one other term here, and that's work. This in the formula is work done Sorry, just triple checking my notes real quick. This is the work done by the system. By the system. So, let's say I add 1,000 joules of thermal energy to something. And as that happens, the object is able to use that 1,000 joules of thermal energy to do 1,000 joules of work. So, when I do work on something, I'm giving it energy. When the object in question here, so let's say I'm going to give a sample object, a common object where heat is introduced to get the object to do work is a piston. So this is like a pneumatic piston that you might find in a car or in a factory. The way that these work is you will add heat into the piston. That heat will warm up some fluid inside of the piston. That will cause the fluid to expand and the piston will extend. Subsequently, you can take heat out of it and that will cause the piston to retract back in. So, if you add thermal energy into this object, this piston will extend and the system will do work. So, let's say I add 1,000 joules of thermal energy to this object and it is able to do 1,000 joules worth of work out of itself. 1,000 minus 1,000 tells me that the internal energy of the object didn't change. I put energy into it, it exported, it sent out the same amount of energy. But let's say I added 1,000 joules of heat and the system only did 900 joules of work. Then the internal energy of the object would increase by 100 joules because I added energy that is still inside of it. It only output 900 joules to do the work. So there's still 100 joules left inside of it that it didn't have before. Its internal energy increased by 100 joules. Now, subsequently, if the system has work done upon it, say someone comes in and pushes on the piston to push it inwards, that's work done on the system, which means you would have to plug in a negative number. If the system is doing work, then you're going to plug in a positive number. If work is done on the system, then you'll plug in a negative number, and these negatives will cancel because that's more energy being added into the object. So, moving on to slide number 7, we're going to do a couple examples with this, very similar to the ones I already talked about. So, for example 1, let's say that we have the same piston as before that I just mentioned. This is a pneumatic cylinder, and the 600 joules of thermal energy is added into this cylinder. The cylinder then expands and does 400 joules worth of work. The question is, what is the change in internal energy of the object during this process? So, delta U equals Q minus W. Delta U is going to be equal to 600 minus 400. Delta U is going to be 200 joules. So, we added 600 joules of thermal energy into the cylinder. The cylinder then expands. In general, whenever you heat something, it is going to expand. The cylinder expands, and as it pushes out, it pushes against something, and it does. We accomplish 400 joules worth of work. Pretty much the goal of any machine is always going to be to, you put energy into the machine in some form, and the machine then does some amount of work for you. All of our machines exist to do work for us. So, like this piston in a factory, it exists to push something. It's going to push something, it's going to exert a force against it. It is doing work on our behalf. So in this particular case, we powered this system with 600 joules worth of energy. We only got 400 joules worth of energy back out. We put in 600 joules worth of heat to power it. It only accomplished 400 joules worth of work. That tells us that the internal energy of this system, it went up by 200 joules. There is now 200 leftover joules of thermal energy trapped inside of the system that is not accomplishing anything. Nothing at all. It's not doing any work. We can't get it back to do anything with it. It's just there. And that plays into the idea of entropy. This is now energy that is, it's not doing work. This didn't do work. We only got 400 joules worth of work. This energy is now just in the object, in the form of thermal energy, not accomplishing anything. This is like when you rub your hands together and they warm up. You are doing work, you are using energy to do this, but it's all going into thermal energy in your hands. You aren't accomplishing anything, you're just creating thermal energy which is now inside of you. That has increased the random, chaotic nature of your system because now the particles in your hands are moving around faster and you have not accomplished any work. So that's what this means. The system, the thermal energy level in the form of thermal energy of this cylinder has gone up by 200 joules. and we didn't get any extra work out of it in order to do anything. The second question on this particular slide says that we are going to we're going to do work into this piston equal to 1,000 joules. We're going to push into this piston with 1,000 joules worth of work. Now, for this formula, work is a positive number if work is positive if the system is doing work. If this piston does work, we plug in a positive W. This is work being done into the piston, not by the piston, which means we plug in this is going to be a negative number. This is negative 1,000 joules. This is not work that the piston did. This is work that was done to the piston. To the piston. So, we are told that the system's internal energy did not change during this time. Did not change during this time. And we are asked to find how much heat the system gained. So, let's go back to our formula. Delta U equals Q minus W. Delta U is 0. 0 is equal to Q minus negative 1,000. Now this is minus negative 1,000. That means this is going to become plus 1,000. But we're going to subtract that over to the other side, and so our final answer is going to be, I'm going to put it down here because there's more space, Q equals negative 1,000 joules. Now the negative here means that the system lost thermal energy. Thermal energy exited this piston. So, in this particular case, we did work on the piston. We added mechanical energy into the system. In order for the piston's internal energy to remain constant when we add this energy in, it has to vent some of the energy it already has. If we put 1,000 joules in and its own internal energy doesn't change, if its total internal energy doesn't change when we add 1,000, it has to get rid of 1,000 to make sure that it stays level. And so what this would mean is as we push this cylinder in, it's going to just vent 1,000 joules worth of heat out of itself in order to maintain its own internal energy level. That's what this example would physically represent. And that's a few different samples using this particular formula. So, the total energy in a system cannot change. The total energy in an entire system cannot change. Even up here, this piston might have increased its internal energy level by 200 joules, but if you think about it, we added 600 joules worth of heat into the piston. So it had a certain amount of energy. We added 600 joules in. It did 400 joules worth of work. That means it kept 200 joules. So all 600 of those joules we added are accounted for. Additionally, those 600 joules entered the piston from outside of the system, and something outside the system had to give up those 600 joules in order to add it into the piston. So, the total energy level everywhere cannot go down. There's a certain total amount of energy. You can trade what object has it, you can trade what form it's in, but the total energy level stays the same. All right, so moving on to slide number 8, we're going to talk about the second law of thermodynamics. This talks about entropy. Entropy, again, is just a fancy term for chaos or randomness. A system that has more entropy is more chaotic internally. And when we say chaos, we mean that its particles, its subatomic particles, are moving around more rapidly and more randomly. So, objects at higher temperatures have more entropy. They're more chaotic. At lower temperatures, the particles of objects are moving around more slowly. Therefore, they have less entropy. It's less chaotic in there. Now, what the second law of thermodynamics tells us is, just like there's a certain amount of energy in the universe that doesn't go down, the energy just changes forms and changes what object it's in, the total amount of entropy in the universe also does not go down. It only stays the same if you don't create any new thermal energy in a process, or it will only ever go up if you do if you do transform energy into thermal energy as a part of a process. Now, we live in a world with friction. And because of friction, every single thing you do, every single time you move, like when I move my arm right now, there's friction inside of my arm. Muscles move across each other, bones move against each other in the joint. There's physical contact inside my arm between the moving parts. And so say I'm using 10 joules worth of energy to move my arm right now. Maybe 9 joules of that energy is actually becoming kinetic energy in my arm, but because of friction, I've lost some of that energy into a thermal form. So say there's 1 joule of thermal energy now in my joint because there's friction there and I can't avoid it. I'm using 10 joules worth of energy, but I'm only getting 9 joules worth of work out of it. 1 joule just becomes lost as pointless thermal energy inside of the works. Because I have transformed some energy into a thermal form, that means that thermal energy is now within the particles of my arm in a thermal state. That means it's making the particles of my arm move around more chaotically. Therefore, I have increased the entropy in my arm. Now, over time, that thermal energy is going to transfer out of my arm, and it will enter my clothes, my skin, the environment around me. And so, as my arm cools down, the entropy of my arm will drop, but the total entropy of the universe will not, because that thermal energy is still going to exist. It's going to go into other places, like my clothes or the air. And it's going to increase the thermal energy level of those things, thereby increasing those objects' entropies and keeping the total amount of entropy in the universe either the same or increasing it. Every process is going to create some waste product of thermal energy. That thermal energy is what increases entropy, and you can't undo it. You can spend some energy to move it around. You can move the energy around. You can move the thermal energy around. You can move the energy, you can move the entropy around, but the total remains the same. There's a quote at the bottom of this page: you can't shovel manure into the rear of a horse and expect to get hay out of its mouth. There are some processes that you can't undo. Like when I move my arm, if I use 10 joules worth of energy, in that process, if I only get 9 joules of work out of my arm, I have irreversibly turned some of that energy into thermal energy. So again, to put it in form of our previous equation, if my internal energy level drops by 10 because I'm using 10 joules worth of energy, my arm will try to do 9 joules worth of work, but that last remaining joule becomes thermal energy in my arm, heat. I can't undo that. I can't turn that thermal energy back into mechanical energy. It's stuck. Just like you can't turn the manure back into hay. You have to exert energy yourself. You have to let that energy go somewhere else. That will decrease the entropy of your system, but like your arm, but it won't decrease the entropy of the entire universe because it still has to go somewhere. It still exists. Like with the hay example, you can move the manure out of your barn, but that manure still exists. You have to use energy to move it out of your barn, and the nature has to go through using time and energy to turn that manure into dirt to let it grow into new grass. So, entropy is always going up because of friction in processes. Every single process creates some thermal energy, and that's going to drive up the entropy of the universe. If you move on to slide number 9, we have a formula, for how to calculate the change in entropy of a specific object or a specific system. So, this formula is change in entropy, that's delta S. We use capital S to represent entropy. So, change in entropy is equal to the heat you add into a system divided by that system's constant temperature. So delta S is the change in entropy of a specific system. We measure entropy in terms of joules divided by Kelvin. Q is the heat added into a system. Heat is measured in joules, thermal energy is measured in joules. And capital T is the constant temperature of the system, measured in Kelvin. You have to use Kelvin for this formula, and I'll show you why in a second. Now, there's a second formula on this slide, and what it says is the change in entropy of the entire universe is either equal to 0 if you manage not to transform any new thermal energy. If everything stays the same, entropy will remain constant. But if any process transforms energy into thermal energy, and there's more thermal energy in the universe than there was before, that causes the entropy of the universe to rise. So that's what that second formula on this slide means. If we move on to number 10, we have some entropy examples. So, we have two separate objects. We are going to add, so the problem says we add 10 joules worth of heat into two different objects. So we have two objects, and we're going to add, Q is heat added, we're going to add 10 joules to both of them. So there's two objects, so there's two separate temperatures to keep track of. One of them is 0 degrees Celsius, the other is 100 degrees Celsius. And the question is, which one gains the most entropy? Which one gains the most entropy? So, if we look at our formula, delta S equals Q. In this case, we are adding 10 joules worth of heat. So we've got change in entropy 1 for the first object, change in entropy 2 for the second object. Just going to make this delta look a little more like a triangle. Both objects are gaining 10 joules worth of thermal energy. Now, if we plugged in their Celsius temperature, we would be dividing 10 by 0. That does not happen. That does not make any sense. The entropy of this system is going to go up. Just because it's at 0 Celsius, the freezing point of water, does not mean its entropy is not going to rise. Because using 0 is not an adequate measurement of how much thermal energy is in the object. Ice at 0 degrees Celsius still has thermal energy in it. It can still get colder if you remove some of that thermal energy, which is why we have to use kelvins for this. So, to take Celsius and turn it into kelvins, you just need to add 273. 273 plus 0 is 273. Meanwhile, 100 plus 273 is 373 Kelvin. So that's what we plug in here. And now we can solve for the increase in entropy of our two objects. Now I'll pull out the calc. No. So, looking at these, the warmer object, you're dividing by a larger number. You're dividing by a larger number for this warmer object. That means the change in entropy of this object is actually going to be less. The colder object is going to gain more entropy. That is because, since it is colder, it's more orderly already. The colder object is more orderly than the warmer object. And so, in gaining this 10 joules, proportionately speaking, its chaos, its randomness, is increasing proportionately more than this object, which already had a lot of entropy. It already has a lot of chaos in it. But this is how you find the change in entropy level of the objects in question. Now, I'm going to reverse this a little bit and ask hypothetically what would happen if instead of adding 10 joules of thermal energy, we took 10 joules of thermal energy away from the system. Q is normally heat added in, so if we take heat out, it becomes a negative number. So these both become negative numbers. If you remove thermal energy from an object, you are going to decrease its entropy level. Decrease its entropy level. So these will be negative numbers, meaning the object lost entropy. But that does not mean the entropy of the universe went down. It just means that entropy has gone somewhere else. That energy has gone somewhere else. It's a very important thing to be aware of. Now, keeping with that, moving on to slide number 11, this is talking about the third law of thermodynamics. The third law says that the entropy of a system approaches a constant value as its temperature approaches absolute zero. That's the long science version of it. The short version is, if something's temperature is at absolute zero, then its entropy will be at absolute zero. If you look at this formula here, if temperature was zero, you're dividing by zero, there's no entropy. An object at absolute zero, at its absolute coldest, its particles are not moving. At absolute zero, an object has no thermal energy, which means its particles are not randomly moving. That random movement is the entropy. It is the chaos. And so, without that random movement, you have no entropy. So the only way to reduce anything's entropy to zero is to get that object to absolute zero. Now, realistically, we can't actually get a whole object to absolute zero. That is so impossibly cold that we cannot actually create an object at that temperature. We can't keep an object at that temperature, and we definitely could never experience that ourselves, because at that temperature, you would become ice immediately. But if you remove thermal energy from something, if you decrease its temperature, its entropy is going to go down. Now, that entropy is being stored somewhere else. If we take 10 joules away from this system, that 10 joules and that entropy has to go someplace else. It still exists, it's just in a different object. So the total entropy either stays the same or rises. The entropy of one object can drop, but the entropy of the entire universe as a whole has to remain constant or rise. And those are the the four laws of thermodynamics. Okay, now we've got two more small concepts to talk about before we wrap things up for Chapter 8 and heat and thermodynamics. The first is thermal efficiency. Now, if you remember from earlier, I mentioned an example of a pneumatic piston where we add 600 joules worth of heat into the system. The piston then expands and does 400 joules worth of work. Now, we determined that the internal energy of the piston would increase by 200 joules because we added 600, it only did 400 joules worth of work. This energy is now just trapped inside of the cylinder as thermal energy, as internal energy that we cannot utilize. It was not used for work. But these pair of numbers here tell us the efficiency of this machine. All machines have various factors that limit how energy efficient they are. For any given machine, if you put a certain amount of energy into it, you'll only get a certain amount of work out of it. And how you determine the efficiency of a machine is with this formula. To calculate the efficiency of anything, which we abbreviate to INF, that's N underscore TH, so INF is the efficiency, you divide the work you get out divided by the energy you put into it. So if we were going to solve that, if we were to find the efficiency of this piston that we just used in the previous example, it did 400 joules worth of work after we gave it 600 joules worth of energy. We gave it 600 and only did 400. So its efficiency is equal to 2/3. It is 2/3 efficient. Now, this 2/3 right here, we could change this to say like 0.67. That's the same as saying 67% efficient. This fraction, this is a percentage. We gave it so much energy and it was able to use 67% of that energy in order to do work. All machines have an efficiency score like this. If a machine was theoretically able to take every joule of energy you put into it and do work with it, it would be 100% efficient. If I had a machine that I could put 10 joules of energy into it and it did 10 joules worth of work, that machine would be 100% efficient. It'd be 10 divided by 10, which is 1. 1 out of 1 is, it wouldn't be, the number you get out of this is always a fraction, 0 to 1. It's a percentage. It's a percentage efficiency. So 10 divided by 10 would be 1. 1 times 100% would be 100%. If I give a machine 10 joules of energy and it does 10 joules of work, it is 100% efficient. But in the real world, no machines are 100% efficient because every machine suffers from energy loss in places, mostly due to friction. Your own body is a great example of this. You ingest energy in the form of food. Your body transforms that chemical energy into mechanical energy to be able to do stuff. But in doing so, some of that energy becomes thermal energy. This keeps us warm, but it does mean every piece of food we eat does not become energy we can use to move. In fact, the human body only has an efficiency of about 20%. If you eat 100 joules worth of food, you'll only get about 20 joules worth to actually be able to move around. The rest of that 80% just becomes heat. So the human body is not actually very efficient. The human body is only about 20% efficient. That means only 20% of the food you eat becomes available as energy that you can use. Additional example, we're going to do a problem on slide 13. So I'm going to put this in a different color over here. So 1 kilogram of coal, which is a lot. 1 kilogram of coal, if you burn 1 kilogram of coal, will produce 24 megajoules worth of energy. The big M is mega, not milli. Megajoules are big, millijoules are tiny. This is a lot of energy. There's a lot of energy inside of a whole kilogram of coal. For context, 1 lump of coal is maybe like 10, maybe 100 grams. A kilogram is a lot bigger. So, we burn 1 kilogram worth of coal in, say, a train, in a coal-fired train. We burn a whole kilogram of coal, which means we release this much energy to be used into the train. The train only does 10 megajoules worth of work. The train does 10 megajoules worth of work even though we fed it 24 megajoules. So, first question, how much energy became internal energy? Well, internal energy is equal to Q minus W. So, it's going to be 24 minus 10. So, delta U is going to be 14 megajoules. We gave it 24, it used 10, and that means it has 14 megajoules left just in the form of thermal energy inside of the train, not doing any work. The next question is, what is the efficiency of this train? So, efficiency, that's inf, is equal to the work out over the energy in. So we gave it 24 megajoules of energy. It only did 10 joules worth of work. So this is the fraction. This fraction represents our efficiency. This train is 10 over 24 efficient. Which is not very efficient. Well, it's less than half, which is more efficient than the human body. This is, I would say, about maybe 30% efficient. Yeah, let me grab my calculator real quick. I didn't work this one out in my head ahead of time. Sorry, everybody. 10 divided by 24. Okay, so that 10 divided by 24 is going to be 41.7. No, sorry, 0.417. So 10 divided by 24 is 0.417. But if we multiply by 100%, turn it into a percentage, that's going to be 41.7% efficient. The human body is about 20% efficient, so a train is about twice as efficient as the human body, but you're still losing a lot of energy. This train has a lot of thermal energy in it that's not being used. So, aim for higher efficiencies in any machines you ever build. Word of the wise. Now, the last heat and thermo topic. This is the last thing that we will discuss before the test next week. This is the last thing to be added onto the test next week. It's about thermal conductivity. Thermal conductivity. So, thermal energy can transfer from one object to another. Heat is always going to flow from hot to cold. So, if I'm really warm and I touch the cold whiteboard, thermal energy is going to transfer out of my hand and into the board. I will perceive this as feeling cold. You don't really have a thermometer in your fingertips. You cannot detect the temperature of an object you're touching. All you can detect is if heat is leaving you, in which case you feel cold. You can also detect if heat is entering you, in which case you'll feel warmth. Now, in general, all thermal energy is going to travel from hot to cold. If one object is warm and it's touching an object that is cold, if they are touching, thermal energy is going to conduct from one object into the other object. So, a quick example. Let's say you've taken a pot of water and you've placed it upon the stove. This is a pot of water. You're going to boil some water to make some pasta, and you're placing it on the stove. The stove has a red-hot heating coil on it. This heating coil is very, very warm. Let's say this is something like 300 degrees Celsius. Meanwhile, the water is only 25 degrees Celsius. Heat is going to transfer from hot to cold. When you place the pot onto these coils, they are in contact. That means that thermal energy is going to conduct from the hot object into the cold object. So, the coils will lose thermal energy, the water will gain thermal energy. Its temperature will rise until it begins boiling, and then you can make your pasta. Now, when two objects are at the same temperature, there's no longer any flow of heat. If you touch something that is the same temperature as you, you will not detect any heat leaving you, you will not detect any heat entering you. It's the same temperature, there's no net flow, you won't feel anything. All of these things, the conduction of thermal energy between objects and the rate at which it conducts, is referred to as just that, thermal conduction. And there is a way to calculate the thermal conduction for any system. The formulas for that are on slide 15. I'm going to put the important ones up on the board. The important ones that you absolutely need to understand up on the board, and we're going to explain them. So, thermal conduction is the rate at which thermal energy transfers. It's the rate at which thermal energy transfers. And it's defined as Q divided by T. Energy, heat flow, divided by time. It's how much, now delta T, sorry, change in time. It's how fast, it's the speed at which heat flows. And because this is energy over time, that makes it power. If you recall from our last test, power is defined as the use of energy over time, the rate at which energy is used. And so, since this is energy moving over time, thermal conduction is a form of power. It's the flow of energy. So, to define everything we have over in this formula so far, the big P is power. And in this case, that is the rate of energy flow. And just as before, power is measured in watts. Power is measured in watts. Next we have Q, that is the heat transferred. That's measured in joules. And then we have delta T, that is the time elapsed. Measured in seconds. That's the time it takes this amount of thermal energy to transfer. And if you divide the thermal energy by time, that tells you the rate at which the thermal energy is going to transfer from one object to the other. So, let's just say it takes you 1 minute to boil your pot, for your water to come up to boil, and in that amount of time, you transfer 100,000 joules worth of thermal energy into the water. To calculate that thermal conductivity, that thermal power, you're going to take the thermal energy transfer divided by the time it took. But remember, we like seconds for time instead of minutes, so you would plug in 60 seconds. And this would tell you the rate at which all of this thermal energy entered the pot. Now there's one other formula on this slide that is very important to know. That is the one closest to the bottom, which I will describe. So, now it's still power. This is the same power. It's a second way to find power, to find heat conductivity. K times A times Ch minus Tc divided by L. So the P is still power. P is still energy flow. A is the surface area measured in meters squared. So that would be the amount of surface area of the bottom of the pot touching the heating coils. If an object's surface area is bigger, that gives it more space for energy to flow through it. So, for instance, if I touch the board with just my pinky finger has a very small surface area, and so heat is going to transfer from my pinky into the board very, very slowly. You don't feel a huge temperature difference here. But if you use the whole palm of your hand, that's a lot more surface area. A lot more energy is going to transfer a lot faster because there's more space for all that energy to come out through. So that's going to feel colder to you. Next, we have Th. That's the hot temperature of the hot side. And for that, you're going to want to use degrees Celsius or Kelvin. Tc is the temp of the cold side. Also degrees Celsius or Kelvin. So if you were looking at this pot of water, This is the temperature of the hot side. This is the temperature of the cold side. So this would be 300. This would be 25. You have to use either Celsius or Kelvin here. You cannot use Fahrenheit. Lastly, we have L, the length the heat must travel through. And that's going to be measured in meters. So, for the case of this pot, the bottom of the pot has a certain thickness, like a centimeter. The heat has to transfer through that length. It has to go through all 1 centimeter of the bottom of the pot. This is that length. The longer the heat has to travel, the slower it's going to be. Notice the L is on the bottom. If L gets bigger, if you're dividing by a large number, P is going to get smaller. If you had a really thick wall to your house, if the walls of your house are several feet thick, it would take a very long time for heat to transfer out of your house during the winter or into your house during the summer. So the thicker your walls, the better insulated your house will be. This formula is useful for determining how well insulated something is. You want the walls of your house to be very well insulated. If something is well insulated, it's going to have a low thermal conduction rate because not a lot of energy transfers through it per unit time. The higher this number is, the faster heat will transfer through it, which is bad for the walls of your house where you want the temperature inside your house to stay nice and constant and cozy. Now there is one more variable in this formula, and that's this K. So I'm going to put that in a different color here. K is the thermal conduction constant. So if you remember before, we had C for specific heat, and that represented how much thermal energy a material needed to warm up. This is a different constant, which represents how quickly thermal energy transfers into or out of a specific material. Every different material has a different K constant. You don't need to memorize them because you have a table right here on this slide, table 11.3. This chart will tell you the thermal conductivity constant of a lot of different materials. So in any of your homework, any of your quiz, you can look at that chart. The problem will tell you what the material is made of, and you can use this chart to find its K value, which we will do now in an example. So, we're going to put some numbers, some different numbers to this one. We're going to put some different numbers to this example. So, we have a copper-bottomed pot. We know the pot is made of copper. To transfer ice cold, it's filled with ice cold water, and the stove is at 300 Celsius. I should have kept that one the same. The stove top is at 300 Celsius. This is the hot side. Ch is 300 Celsius. This is the hot. This is the burning element. Meanwhile, the water on the cold side, it is ice cold, meaning it is at 0 degrees Celsius. This is the cold side. The pot has a thickness, so length through it. The bottom is 2 millimeters thick. Now we need to turn millimeters into meters. That's going to be 0.002 meters. And we are told the diameter of the pot is 12 centimeters. If we turn centimeters into meters, that's going to be 0.12 meters. But we don't need diameter, we need area. So, it is completely okay to look up the formula for area of a circle. The formula for area of a circle is pi r squared. This is a known formula. It is okay if you write it down. It is okay if you look it up. So we need to find the area of the bottom of this pot. So area is equal to pi, which is 3.14, times the radius of the pot squared. Radius is half of diameter. So make sure to cut your diameter in half and then square it. That's it. That's going to give us an area of approximately 0.011 meters squared. That is the area of the bottom of this pot. Now the question asks us, how much power will transfer through this pot? Again, power is the rate at which thermal energy flows. So we're solving for P. We know A. We have found A. We know the temperature difference between the hot and the cold side. We know how thick the pot is. Now we just need K. We need to know what the K constant for this pot is. Now the problem told us the pot was made of copper. So we can go back to slide 15, look at our chart, and it says the thermal conductivity for copper is 397. So that is the variable that we can plug in for K. So power is going to equal K, which is 397, times area, which is 0.011, times the temperature difference. It's going to be 300 minus 0, then divided by the thickness of the pot. And that is going to tell you the power transferred through this pot. So, that is our last, that's the last one I have for this video lecture. This is, Chapter 8 will be the last thing on the test next week. Please watch this video lecture as soon as it goes up. That'll be Friday. What I want for us to do is, let's meet on Monday for our class call. I will address any questions, any concerns you have about anything from these slides, because I know we went through a lot of information very quickly. I'll address any questions you have. We will get everyone ready for the test, which, if you are absolutely ready, you can try to take it Monday, but I recommend waiting to either Tuesday or Wednesday. So, Tuesday or Wednesday, you can email me when you're ready to start your test, and I'll send you the document like I did last time. Those will be our test days. From that point on till the end of the week, I will upload the last couple of topics that we need to cover for this semester, and those will end up into the final exam. We will spend the end of next week going over those, getting everyone ready for that exam. Please come to our class calls. Please ask me literally any questions you have at any time. Email me, invite me to a Google Meet, attend our class calls, and we'll get everyone ready. Thank you guys so much, and have a wonderful day.